Photoelectric effect example. So, yesterday when we were talking about the photoelectric effect, we were talking about how the equation HF, or as we I think wrote, H nu, whatever, it's a frequency, can be equal to the kinetic energy max of a released electron from sort of like from a salt plate plus the amount of work that is done, or some minimal threshold work that is needed to cause this to happen for like an outer shell electron. Now, we can take this idea and we can find the kinetic energy and the velocity of an ejected electron from a sodium surface with a known work function. If it's illuminated by light of 410 nanometers, which is actually closer to like a violet or a purple light, or by light that is 550 nanometers, or like a green light. And we can use this equation to do this. So let's try to work this out. The first thing we'll do in part A for the 410 nanometer light is we need to recognize that this H nu, that is an energy of the light. Okay, that is the energy. So we know that the energy of a photon of light is given by H nu, or HF, however you want to write it. Now, something that we should note is we're not given frequencies in this problem. We're given values in nanometers. These are wavelengths. Ugh. But wavelengths are often how we think about electromagnetic radiation. It's often how we think about light. So something we have to recognize here is that the wavelength multiplied by a frequency is going to be equal to c, the speed of light. Which means nu, or the frequency, can be thought of as the speed of light divided by the wavelength. So let's take this quantity, c over lambda. Let's put it back up into our energy equation. Doing this then, this equation can be written as hc over lambda. Now, before you start busting out your calculators like there's no tomorrow, here's a helpful little trick. This hc, Planck's constant, multiplied by the speed of light, those are two constant values there. And hc comes up a lot. It actually comes up so much that it is worth your time to remember that hc is equal to 1240 electron volts nanometers. And this is so helpful for us because when we divide by the wavelength, which just happens to be in nanometers, the nanometers divide out. And we get a value that's in electron volts, which is an appropriate unit of energy, and it is what our work function was given in anyways. So Hc equaling 1240 eV is extremely useful for us moving forward. Otherwise, we have to remember both 6.626 times 10 to the negative 34 and 3.0 times 10 to the 8th. Too many things to memorize. Let's just go with the 1240. If we crush this on a calculator, much more straightforward, 1240 divided by 410, this gives us about 3.02, 3.03, we'll put 3.02 EV. Now, if we use our equation, we can simply say 3.02 EV equals the max kinetic energy plus that work function. 2.28 eV. Solving for kinetic energy max by subtracting 2.28 on each side, we find that the kinetic energy max is equal to 0.74 electron volts. Now, if we want to put that back to joules in order to get ourselves a velocity at the end, because EVs aren't an SI unit, then all we'll have to do is multiply that by a conversion factor. We know there's 1.6 times 10 to the negative 19 joules in 1 EV. We actually learned that way back when we talked about electrostatics and electromagnetism. That was one of our conversions. And in doing this, we should get a value of, if we round up, of about 1.2 times 10 to the minus 19 joules. So while a 0.74 EV is a correct value for the energy, if we need to find a velocity, which we're asked to do in this problem, then we need to go get a value in joules so that we can get our proper SI units out. Okay? At this point, if we wanted to find that velocity, we know how to do that with the kinetic energy. We know that kinetic energy is just equal to 1/2 multiplied by the mass of the electron multiplied by velocity squared. If we want to solve this here for velocity, we're going to find that the velocity is just equal to the square root of 2 times the kinetic energy, 1.2 times 10 to the minus 19, divided by that mass of the electron, which is 9.11 times 10 to the negative 31st. Careful when you're entering all this into your calculator. We've got a lot of funny numbers here. The times 10s we should be using the big E's on. Make sure you're doing your numerators and denominators separately, then dividing them, then rooting them. It's a whole lot. But when I crunch out the numbers, I find something approximately equal to 5.1 times 10 to the 5th meters per second, with a little bit of rounding. This is pretty fast, but note, it is still much, much less in terms of speed than the speed of light. So we don't have to worry about any relativity or like any weird effects due to that for moving super fast, because while we're moving quick, we're not moving at speed of light levels yet. Okay? In part B, we do this same thing, but for light at 550 nanometers. So let's figure out what the energy of this light is. Hc over lambda is 1240 over 550. That's going to give us an answer in EVs. 1240 divided by 550 is 2.25 electron volts. Notice here that this energy given by the photon of light, it is less than the work function. This means that no electron will be released from our sodium salt plate, which means that there's no kinetic energy. Our photon of light striking that salt plate didn't have enough energy to release this electron. So no electrons ejected. And part B is now complete. Whew! Part B is much easier than part A. We didn't have enough energy there. We didn't have a short enough wavelength or a high enough frequency to get enough energy out in this scenario. Okay? So that's just a quick little example of what our photoelectric effect is doing, how we think about it, how we use this equation. we have a pretty good idea of what that equation is to begin with. The big takeaway in this problem is don't forget about this HC. It equals the 1240 EV nanometers. That's a super helpful thing to solve problems quickly. And then using that and understanding what this means is everything. So with that, this problem is finished. Until next time, adios, and take it easy.